welcome back. This lecture is a continuation of last lecture wherein we introduced vapor compression refrigeration systems and we discussed saturated single stage standard cycle, that is SSS cycle, and we compared the performance of that cycle with an ideal Carnot vapor compression refrigeration system. And we have also given some basic equations for evaluating the performance of this system. So, we will continue in this lecture starting with the performance aspects of SSS cycle, and we will also discuss the various modifications to the standard cycle. So, the specific objectives of this particular lesson are to discuss the performance of SSS cycle, introduce subcooling and superheating, discuss vapor compression refrigeration system with liquid suction heat exchanger, discuss effect of superheat on system performance, discuss the differences between theoretical and actual cycles, and discuss a complete vapor compression refrigeration system. So, at the end of this lesson you should be able to evaluate the effects of evaporator and condensing temperatures on the performance of a SSS cycle, evaluate the effects of subcooling and superheating using TS and PS diagrams, evaluate the performance of modified vapor compression refrigeration system with liquid suction heat exchanger, and find whether superheating increases COP or not using a simple criteria, and discuss various irreversibilities in actual systems and their impact on performance. So, let us begin with the performance of SSS cycle. The performance can be obtained from the simple analysis presented in the last lecture and using suitable property data. And typical performance trends show the effects of evaporator and condenser temperatures. What is normally done is we keep the condenser temperature constant and vary the evaporator temperature and find different performance parameters. Then you keep the evaporator temperature constant and vary the condenser temperature. So, in that manner you can find out the effect of both condenser as well as evaporator temperature on different performance parameters of interest. Okay, let me show now the effect of these temperatures on different performance parameters. The first one is the effect of these temperatures on specific and volumic refrigeration effects, and then specific and volumic works of compression, then system COP. So, first let me show the effect of the temperature on refrigeration effect. So, this QE is a specific refrigeration effect. As you can see, it has unit of kilojoule per kg, and QV is volumic refrigeration effect, that means refrigeration effect per meter cube of refrigerant flow. And you can see here that on x axis I have evaporator temperature, and I have got these performance parameters for different values of condenser temperature. So, you can see that condenser temperature is increasing in this direction for specific refrigeration effect, and it is increasing again in the same direction for volumic refrigeration effect. So, from this graph you can easily see that as you are increasing the evaporator temperature for a given condenser temperature, there is a marginal increase in specific refrigeration effect. Okay. And the specific refrigeration effect also increases as condensing temperature decreases. Okay. That means QE increases as TE increases and TC decreases. But as I said, this effect is not very large, it is marginal. That you can easily find out from this pH diagram. As I have already discussed in the last class, this is your refrigeration effect or this is your QE. Okay. So, if you are keeping the condenser temperature constant and if you are varying the evaporator temperature, for example, I am increasing the evaporator temperature, that means this line shifts up. Okay. So, and you have the new cycle like this. So, what is the increase in refrigeration effect is very small. You can see that is only this much. Okay. So, this purely depends upon the slope of this saturated vapor curve on pH diagram. Okay. And you can see that it is almost vertical. So, the change in QE with TE is marginal. And what happens when you are reducing TC? You can see that, for example, when I am reducing the TC, you have reduced TC like this. So, your refrigeration effect now increases and it becomes larger. Okay. So, that you can very easily verify with the help of this pH diagram. Okay. And you can also see the effect of these temperatures on volumic refrigeration effect. So, how did we define volumic refrigeration effect? If you remember, QV is defined as H1 minus H4 divided by the specific volume of the refrigerant vapor at the inlet to the compressor. That means specific volume at at this particular point. Okay. Now you can see that for a given condensing temperature, as you are increasing evaporator temperature, specific volumic refrigeration effect increases very rapidly. You can see that by this dashed line. Why does it increase rapidly? Because you can see that there are two effects here. First effect is this. Okay, as TE increases, specific refrigeration effect increases marginally. So numerator increases. Okay, at the same time, when you are increasing the evaporator temperature, the specific volume of the refrigerant vapor decreases steeply. Okay, so numerator is increasing and denominator is reducing steeply. As a result, you can see that the volumic refrigeration effect increases quite rapidly with evaporator temperature, and it reduces as the condenser temperature is reduced. So what is the practical consequence of this? The practical consequence of this is, if you are operating your system at high evaporator temperature, your volumic refrigeration effect is very large. That means the required size of the compressor will be small, because remember that in the last class I have mentioned that this is an indication of the size of the system for a given refrigeration capacity. Okay, so higher the evaporator temperature, smaller will be the size of the system. Conversely, when the evaporator temperature is very small, you end up with a very large and bulky compressor. Now let us see the effect of these temperatures on other performance parameters. So this graph here shows the effect of evaporator and condenser temperatures on specific work of compression. Okay, that is work of compression per kg of refrigerant, and this is volumic work of compression. Again, we have defined this in the last class. Okay, if you multiply the specific work of compression into mass flow rate, you get the power, and if you multiply the volumic work of compression into volumetric flow rate, you get the power. Okay, and you can see that for a given condenser temperature, for example, take this condenser temperature, as you are increasing TE, okay, so as you are increasing TE, your work of compression, specific work of compression reduces in this direction. That means specific work of compression reduces as TE increases. Why does it happen? Again, you can easily verify this with the help of your pH diagram. Let us say that this is your original pH diagram, and this is your work of compression. Okay, now if I am increasing this evaporator temperature, then you can see that this will get reduced. Okay, that you can verify even from the earlier diagram also. So, okay, so it has quite a significant effect. So as your evaporator temperature increases, work of compression reduces, and the work of compression reduces as your TC reduces. Okay. Now how about the effect of this on volumic work of compression? Volumic work of compression is again defined as, if you look at the earlier pH diagram, it is simply defined as H2 minus H1 divided by V1, and here you have seen that as you are increasing TE, this is reducing. Okay, and at the same time this also reduces. So both numerator as well as denominator reduces. So ultimately whether this reduces or not depends upon the relative reduction in this over this. Okay, so you can see that initially as evaporator temperature is increasing, the volumic work of compression increases. So it reaches some peak, then it starts reducing. Okay, the same thing is observed for different condenser temperatures, and you can see that this peak shifts to higher evaporator temperatures as the condenser temperature is increased. Okay, so this is the effect of evaporator and condenser temperatures on work of compression. Now let us see the effect of this on COP of the system. Okay, so you can see the effect of evaporator and condenser temperature on COP of the system. So from the earlier two figures, it is very easy to come to this conclusion, because as you know very well, COP is the ratio of your refrigeration effect divided by work of compression. So we have seen that as T is increasing, refrigeration effect increases very marginally, but this reduces significantly. As a result, your COP increases with TE. Okay, and similarly when TC is increasing, this reduces. That means QE reduces as TC increases, and work of compression increases as TC increases. So as a result, COP reduces as your condenser temperature increases. Okay, so one thing you can notice here, just like your effect of performance on Carnot system, you can see that at lower condenser temperatures, the effect of evaporator is quite predominant. That means this curve is quite steep compared to other curves. Okay, so that means at lower condenser temperature, evaporator temperature has a larger effect, and at lower evaporator temperature the effect of condenser temperature is marginal. Okay. So, what do we conclude from this? We conclude from this that if you want to have a good COP and if you want to have a small compressor and small refrigerant flow rate, etc., you have to operate your system at as high an evaporator temperature as possible and as low a condensing temperature as possible. Unfortunately, the evaporator and condensing temperatures it's not in the hands of the designer completely, because they are actually decided by the customer. For example, the evaporator temperature depends upon your storage requirements or your refrigeration requirements, and the condenser temperature generally depends upon the available heat sink. Okay, so you really don't have much say on this, but still you can reduce for example, you can reduce the temperature differences between the heat source and sink and the refrigerant temperatures by designing efficient heat exchangers. Only that is the advantage you get. Okay. And one thing you can notice here, as I have already mentioned, is that the trends here are exactly similar to that of a Carnot cycle. Okay. For example, the effect of TE and TC on COP, it is qualitatively it is same for Carnot cycle as well as the standard SSS cycle. Okay. So, you can this is the conclusions from the performance trends. For good system performance, the evaporator temperature should be high and condensing temperature should be low. At low evaporator temperature, effect of condenser temperature is marginal. The above trends are similar to that of a Carnot refrigeration system. At very low evaporator temperatures, saturated single stage cycle is not viable, because the COPs will be small and required compressor size will be very large. Okay, so in such cases we have to use what is known as a multi-stage or cascade system. Okay, we will discuss the multi-stage and cascade systems in the next class. Okay, now let us look at modifications to standard saturated single stage cycle. What are the modifications? First modification is subcooling. So, let us look at subcooling. What do we mean by subcooling? In actual systems, the temperature of the heat sink will be several degrees lower than the condensing temperature for heat transfer. That means, if you have an actual vapor compression system and let us say that your heat sink is available at 30 degrees, then to facilitate heat transfer you have to operate your condenser at a temperature higher than 30 degrees centigrade. Okay, it may be 31, 32, 33. Right. So, whatever it is, there will be some delta T or some temperature difference between the refrigerant condensing inside the condenser and the external heat sink. Okay. So, some delta T is available. So, it is possible to cool the exit of the condenser to temperatures lower than the condensing temperature by adding some extra area. Okay. For example, you have a delta T of 5 degrees centigrade, let us say. So, if your condenser is operating at 35 degrees and the heat sink is 30 degrees, then if you add some more extra area, maybe you can reduce the condenser temperature to 34 or 33. Okay. At the same time, pressure remains constant. Okay. So, by this process what we are doing, we are actually pushing the refrigerant liquid into subcooled region. Right. If you are not using this, then it will be on the saturated liquid line, and if you are adding extra area, it will go into the subcooled region. Okay. This process is known as subcooling. So, as I said, it is possible to cool the refrigerant liquid to a few degrees lower than the condensing temperature. Then the exit condition of the condenser will be in the subcooled liquid region, and this process is known as subcooling. As the name implies, it is very clear. And subcooling, we shall see, has beneficial effects on system performance. Let us look at what are the effects of subcooling on system performance. Okay. So, here what we have here is 1, 2, 3, 4, cycle 1, 2, 3, 4 is without subcooling. That means 1, 2, 3 and 4. This is without subcooling. So, you can see that the exit condition of the condenser lies on the saturated liquid line. Okay. So, in this cycle we have seen in the last class that there are some throttling losses, okay, and those throttling losses are given by this area 3, 4 F. Okay. That means throttling losses without subcooling, that is equal to area 3, 4 F. Okay. And the same thing is shown on the pH diagram also. For example, in the pH diagram 1, 2, 3, 4 is the cycle without subcooling, and 1, 2, 3 dash 4 dash is with subcooling. Okay, that means what is happening during subcooling? If you are assuming that the saturated liquid line coincides with the constant pressure line, that means this constant pressure line is going along the saturated liquid line, like we have discussed in the last class. Then during subcooling what happens is the pressure remains constant but temperature reduces. So you can see that the exit condition instead of at 0.3 it will be at 0.3 dash, okay, and the temperature at 0.3 dash will be less than the corresponding saturation temperature T3. Okay, and this temperature difference T3 minus T3 dash is what is known as degree of subcooling or delta T sub. Okay, and what has happened because of the subcooling? You can see that because of the subcooling the throttling losses have reduced. Okay, previously the throttling loss was area 34F, now the throttling loss is 34-F. Okay, with subcooling this is the throttling loss, without subcooling this entire area of the throttling loss. Okay, obviously it will have beneficial effect. That will be very clear if you look at the pH diagram. Okay, from the pH diagram without subcooling this is the refrigeration effect, that is H1 minus H4 is the refrigeration effect QE without subcooling. And what is the refrigeration effect with subcooling? That is H1 minus H4 dash is QE with subcooling. Okay, so you can see that it is good because refrigeration effect increases means for the same capacity required mass flow rate reduces and you have all other related benefits. Okay, so subcooling is really beneficial from this point of view. It also has other benefits. Let us look at what are the other benefits. Other benefits are, you can see that the exit condition of the condenser is very much in the subcooled liquid region. So this will always ensure that only liquid goes into the expansion device. Remember that process 3-4 is the expansion process or throttling process. Okay, so when you have when you don't have any subcooling, then the inlet condition is just saturated liquid. If something if some change takes place in the condenser, then there is a possibility that this point will shift this side and the inlet condition will go into two phase. So at the inlet to the expansion device you may have vapor. Okay, it may be somewhere here. We shall see later that this will actually lead to the malfunctioning of the expansion device. An expansion device is designed to operate with liquid entry only, it should not have any vapor. Okay, so the possibility of vapor going into the expansion device exists if you have a cycle without subcooling. But whereas if you have a subcooling, then you can see that there is sufficient margin. Okay, so even if there is some slight change in the condenser heat transfer, still the inlet condition can be in the subcooled region. Okay, so this is the second benefit. So subcooling is desirable from this point of view also because it ensures a good and proper operation of expansion device. The third benefit is that if you remember from your last lecture, at the exit of the evaporator, exit of the expansion device, which is nothing but the inlet to the evaporator, you have some vapor plus liquid. Okay, and that vapor fraction is given by X4. Okay, so larger this length, higher is the amount of vapor. Okay, so when you are subcooling the cycle, you can see that the vapor fraction has reduced. Okay, from 4 to 4 dash, right? Because X4 dash is less than X4. Okay, this is also beneficial. It also has practical benefits because we shall see again later when we discuss evaporators and all. The vapor at the inlet to the evaporator practically does nothing. That means it doesn't take part in providing useful refrigeration effect as long as phase change is going on, but it has a negative effect because it increases the pressure drop through the evaporator. Okay, so normally the smaller the amount of vapor, it is better for the evaporator. Okay, if you don't have any subcooling, you see that the fraction of vapor is large, and by subcooling you are reducing the fraction of the vapor at the inlet to the evaporator, which will reduce the pressure drop in the evaporator and ultimately it will result in better performance. Okay, so subcooling has these three benefits, so it is very much desirable. So let us summarize this. So subcooling increases refrigeration effect without affecting work of compression. Yeah, I forgot to mention this. You might have seen that because of subcooling there is practically no change on the compression side. That means the work of compression remains the same whether you subcool the refrigerant or don't subcool the refrigerant. That means you are getting the benefit of additional refrigeration effect without affecting the work of compression. Obviously this must give rise to higher volumic refrigeration effect and also higher COP, okay, without any extra cost. So, it increases refrigeration effect without affecting work of compression. It reduces the vapor fraction at the inlet to the evaporator, leading to reduced pressure drops in the evaporator. It ensures liquid entry into expansion device, thereby ensuring its proper function. Okay, so these are all desirable, then why not have large amount of subcooling? Ultimately, unfortunately, there are certain constraints. What are the constraints? The degree of subcooling depends on the extra area provided for heat transfer and the temperature of the heat sink. So, if you are trying to provide subcooling by increasing the area of heat transfer, obviously you are incurring additional cost because the heat exchanger becomes bigger, so additional cost. Okay. At the same time, it is also limited by the temperature of the heat sink. As I have mentioned already, the exit temperature of the condenser cannot be lower than the heat sink temperature. Okay. So, ultimately the degree of subcooling that you can get by this method depends upon the extra area you can afford to provide and the heat sink temperature. Okay. Now, let us look at the other modification, that is called as superheating. What is superheating? So, temperature of heat source will be few degrees higher than the evaporator temperature. Hence, the vapor at the exit of the evaporator can be superheated. This is again similar to your condenser problem. If you want to exchange heat from the refrigerated space to the evaporator, you must provide certain delta T. Okay. A typical example, for example, if you want to maintain your freezer compartment of a domestic refrigerator, let us say at minus 18 degrees centigrade, then you have normally they operate the evaporator at about minus 23 degrees centigrade. That means about 5 degrees of temperature difference is provided, so that heat transfer can take place in a finite area. Okay. So, some delta T exists. So, if you can afford to, you can add more area and you can reduce the delta T, keeping the pressure constant. Okay. Thereby what you are doing, you are adding extra area for heat transfer, there will be higher heat transfer to the refrigerant, thereby the exit condition of the refrigerant vapor goes into the superheated region. Okay. So, just like your subcooled this thing, this will go into the superheated region. So, this is what is known as the superheating. Okay. Now, superheating can be, unlike subcooling, superheating can be useful or useless. What do you mean by useful superheating? If the superheating of refrigerant takes place due to heat transfer with the refrigerated space, then it is called as useful superheating. Okay. That means, if this heat transfer is taking place inside the freezer compartment, okay, then it is useful, because the cooling effect is ultimately given to the products. Okay. So, it is, you call it as useful superheating. On the other hand, if the heat transfer is taking place outside the refrigerated compartment, let us say that it is exchanging heat with surrounding air, okay, then you do not get any benefit, right. So, the refrigerant gets superheated, but you are not getting any benefit. Okay. This kind of a superheat is known as useless superheating. Okay. So, as I said, on the other hand, if refrigerant vapor becomes superheated by exchanging heat with the surroundings, it is called as useless superheating. Let us look at the effect of useful superheating. For the let me tell at this point, and I will also show this later, but useless superheating is detrimental to system performance. Okay. So, as far as possible, a system should be designed in such a way that whatever superheating takes place, it takes place in a useful manner. Okay. So, all useless superheat should be avoided. So, let us look at the effect of useful superheat. Okay. So, this figure shows again, just like subcooling, the cycle without and with superheating on TS as well as PS diagrams. Okay. Look at the TS diagram, as I said 1, 2, 3, 4 is without superheating. Okay. If you do not have any superheating, what is the your useful refrigeration effect? This is the useful refrigeration effect. Okay. This area, right. And what is the work of compression? We have seen that the work of compression in fact is this entire area. Okay. So, this is QE and this is your work of compression without superheating. Now, let us say that I have superheated it. Superheated means what I am doing? I am pushing this exit condition from the saturated vapor to a superheated vapor, okay, along the constant pressure line. That means, this is the constant PE line. Okay. So, it is a sensible heat transfer process, assuming that there are no pressure drops, so it is taking place isobarically. So, this point is shifting to superheated region. Remember that you have subcooled region here, two phase region here, and superheated region here. Okay. So, because of this superheating 1 to 1 dash, okay. So, 1 to 1 dash is your superheating. So what is the effect of the superheating? First effect, immediately you see that there is an increase in refrigeration effect, and that increase is given by this area. Okay, so this is the area which is an indication of increase in refrigeration effect because of superheating. Okay, and there is also another effect. What is that? There is also a simultaneous increase in work of compression, and that is given by this area. Okay, so because of the superheating, both refrigeration effect as well as the work of compression both are increasing. Okay, the same thing can be seen from this point also. Without superheating, from pH diagram, without superheating, this is your refrigeration effect. With superheating, this is your refrigeration effect. So you can see that refrigeration effect has increased because of superheating, and without superheating, this is your work of compression. Okay, H2 minus H1, and with superheating, this is the work of compression. Okay, and this will be always greater than this one. Okay, because we shall see later that these lines, the isentropes, they diverge as you move into the superheated region. Okay, you can see that they are diverging. As a result, H2 dash minus H1 dash will be greater than H2 minus H1. That is very evident from this TS diagram. Okay, so we have one positive effect, that is we are getting higher refrigeration effect, and one negative effect, that is higher work input. So ultimately, whether it is good for the performance or not, let us see that. Okay, so first let me summarize what I have discussed. A useful superheating increases both refrigeration effect and work of compression. It also increases, you might have noticed that by pushing the suction condition into superheated zone, the compressor discharge temperature also increases, and since temperature is increasing at the inlet to the compressor at a fixed pressure, the specific volume of refrigerant also increases. That means in addition to refrigeration effect and work of compression, superheat also affects the compressor discharge temperature as well as the specific volume of the refrigerant at compressor inlet. Okay, these are the effects. Okay, now whether the COP and volumetric refrigeration capacity or volumetric refrigeration effect increases or not depends upon the nature of the refrigerant and operating conditions. So you cannot say offhand whether superheating will improve the COP or not. Okay, it is very much a function of the nature of the refrigerant and also to some extent the operating conditions. Okay, so you have to examine each refrigerant and decide whether superheating increases COP or not. Okay. We shall see that a little later. Whether it increases COP or not, some amount of superheat is always used in practical systems to prevent entry of liquid into compressors. So there is a very practical reason why superheat is necessary in actual systems, because just like an expansion device cannot tolerate vapor, a compressor we have seen in the last class cannot tolerate, most of the compressors cannot tolerate the presence of liquid. Okay. So you must make sure that whatever is entering into the compressor is vapor. Okay, no liquid is entering into the compressor. Now if you have a cycle without superheating, that means the entry condition is on the saturated vapor line. Okay, and due to some changes in the evaporator load, it is quite possible that the entry condition can shift into the two-phase region. That means some liquid can enter into the compressor which may damage the compressor. Okay. But if you are providing superheating, even if there is some small change in the evaporator load, still the exit condition will be in the vapor region only. So you are ensuring a safe operation of compressor. Okay. So this is one of the reasons why superheating is provided in almost all systems, whether it increases COP or not. And it is also seen that from practical observations and experimental results that superheating has beneficial effects on volumetric efficiency of the compressor. So because of these two reasons, superheating is provided. But how much superheating has to be given depends again upon the nature of the refrigerant. Okay. And as I have already mentioned, useless superheat is detrimental. Okay. So you must always avoid useless superheat. That means you must avoid heat transfer between the refrigerant and the outside ambient, okay, in the suction lines. This is the reason why all the suction lines are insulated. That means lines going from the evaporator to the compressor have got to be insulated, so that heat transfer between the surrounding air and the refrigerant can be minimized, thereby minimizing the useless superheating. Right. Now let us look at the use of liquid suction heat exchanger. So this is a modification over the simple cycle. Now we have seen that you can provide certain amount of subcooling and certain amount of superheating using the temperature difference available between the refrigerant and the heat source and sink. Okay. But there are certain restrictions, as you have seen, that is restricted by the available heat source and sink temperatures, and also on the additional area that you are providing. Okay. And if you want certain amount of subcooling and superheating, that may not be possible always just by exchanging heat with the heat source or sink. Okay. So one way of ensuring required amount of subcooling and superheating is by using what is known as a liquid suction heat exchanger or LSHX. Okay. So that is what is mentioned here. Required degree of subcooling and superheating may not be possible if one were to rely on heat transfer between the refrigerant and external source and sink. And also, if refrigerant at the exit of the evaporator is not sufficiently superheated, this is another reason why we need a liquid suction heat exchanger. If the exit is not sufficiently superheated, then it may get superheated by exchanging heat with the surroundings, which, as you know, is useless superheating. So a liquid suction heat exchanger can ensure required amount of subcooling and superheating. Let us see what is a liquid suction heat exchanger. Okay, a liquid suction heat exchanger is basically a counterflow heat exchanger in which the warm refrigerant liquid from the condenser exchanges heat with the cool refrigerant vapor from the evaporator. So let me show this. Okay. So what we have here is a system with a liquid suction heat exchanger. In the basic system we had only evaporator, compressor, condenser and expansion device. So in the modified system we have added an extra component, liquid suction heat exchanger. So what is happening in this extra component? In this extra component, the liquid from the condenser, okay, liquid from the condenser is flowing in this direction, okay, and vapor from the evaporator is flowing in this direction. That means they are flowing in opposite directions, okay. And I will show you in the next slide that the temperature of the liquid that is entering into the heat exchanger is much larger than the temperature of the vapor that is entering into the heat exchanger. As a result, this liquid can exchange heat with the vapor. So the liquid becomes cooler and the vapor becomes hotter. Okay, that means if you look at the temperatures, T4, that is the liquid outlet temperature, will be less than T3 and T1 will be greater than T6. That means the liquid is getting subcooled and vapor is getting superheated. Okay. And as I have already mentioned, process 6 to 1 is superheating of vapor and process 3 to 4 is subcooling of liquid. Let me show this one on TS and PS diagrams. So what you see here on the top is the TS diagram and the bottom you have PS diagram. If you do not have any subcooling or superheating, or if you do not have any liquid suction heat exchanger, this is the temperature of the liquid, okay, and this is the temperature of the vapor. So you can see that a large temperature difference exists between the liquid and the vapor. So you can exchange actually heat between these two by using a liquid suction heat exchanger. That is what is happening here, that is what is shown here. Okay. So this case, this is exchanging heat like this, okay, this is the arrow, this is exchanging heat like this. In this process this temperature is reducing and this temperature is increasing, and both the processes are typically almost isobaric. So they take place, this process subcooling takes place along the constant condenser pressure line, and superheating is taking place along the constant evaporator pressure line. Okay. The same thing is shown here also. So you can see that this is your process of subcooling and this is the process of superheating. Okay. This is your superheating, this is delta T, okay, delta T superheat, and this is your subcooling. So what is the effect of subcooling and superheating on the system performance? Immediately one thing is clear, that refrigeration effect has increased. Okay. Without this liquid suction heat exchanger, your refrigeration effect was this much. Okay. This is your delta H, or that is equal to QE. Okay. And because of this liquid suction heat exchanger, now it has become this much. Okay. So that is a benefit, but you will also simultaneously see that there will be some increase in work of compression also, because without subcooling this would have been your work of compression, and with liquid suction heat exchanger this becomes your work of compression. Okay. So both the effects are present. Now let us write some basic equations for this. So what is the heat transferred in the liquid suction heat exchanger? If you apply steady flow energy equation and neglect potential and kinetic energy changes, then heat transferred in the liquid suction heat exchanger is simply given by this heat transfer. This is the energy lost by the refrigerant liquid and this is that is equal to energy gained by the vapor. Okay, so this is for the liquid portion and this is for the vapor portion. And since the mass flow rates are same mass is flowing through both the components, this can get cancelled. So you can simply write this as H3 minus H4 is equal to H1 minus H6, where H3 is the saturated liquid enthalpy, H4 is the enthalpy at the end of the liquid suction heat exchanger, and H1 is the saturated H6 is the saturated vapor enthalpy, and H1 is the vapor enthalpy at the end of liquid suction heat exchanger. And if you are taking some average specific heat values, we can write this as CPL into T3 minus T4, which is equal to CPV into T1 minus T6, where CPL is the specific heat of the liquid and CPV is the specific heat of the vapor. And as you know, generally the specific heat of the liquid is much higher than specific heat of the vapor. That means CPL will be greater than CPV. So from this equation, T3 minus T4 should be less than T1 minus T6. That means delta T subcooling will be generally less than delta T superheating. Okay, how much less depends upon the values of Cp for liquid and Cp for the vapor. Okay, so that's what is mentioned here. Degree of superheating is greater than degree of subcooling, right? Now, if you define the effectiveness of heat exchanger as the actual heat transferred divided by maximum possible heat transfer. Okay, that means I am defining an effectiveness for the heat exchanger epsilon LSHX, which is defined as the ratio of actual heat transfer to maximum possible heat transfer rate. Okay, what is actual heat transfer? If you are writing it for the vapor, this is nothing but the m dot Cp into delta T of the vapor, that is m dot R into Cpv into T1 minus T6. Okay, and what is the maximum possible heat transfer? The maximum possible heat transfer in a typical heat exchanger is for a fluid which has a lower m dot Cp. That means a fluid which has lower mass flow rate into specific heat will undergo the maximum possible temperature change. Okay, so as a result, in our case, the Cp of vapor is less than the Cp of liquid, whereas the mass flow rates are same. So vapor has the lower thermal capacity compared to the liquid. So if at all anything is undergoing the maximum temperature change, it has to be the vapor. Okay, so Q max is nothing but mCp of vapor into delta T max. Okay, that's what is written here. So you can see that this is the mCp of the vapor and this is the maximum possible temperature difference. Okay, what is the maximum possible temperature difference? When the exit condition of the vapor is same as the inlet condition of the liquid. That means when T3 becomes T1, that is the condition under which you get maximum possible heat transfer. Okay, again these two get cancelled. So you have ultimately effectiveness is defined as T1 minus T6 by T3 minus T6. Okay, so you might have studied in heat transfer this thing. How do you evaluate effectiveness in terms of other design parameters? Now, if you take a hypothetical case where you have a perfect heat exchanger whose effectiveness is 1. Okay, that means this is equal to 1. If this is equal to 1, what happens? T1 will be same as T3. And what is T3? T3 is nothing but the condenser temperature. That means by using a perfect liquid suction heat exchanger, you can heat the refrigerant vapor from the evaporator temperature right up to the condenser temperature isobarically. Okay, that means when epsilon LSHX is 1, T exit of the liquid suction heat exchanger will be same as the condenser temperature. This gives rise to an interesting cycle proposed by Grindl, and it is called as Grindl cycle. Let me quickly show the Grindl cycle. Okay, so this is what is shown. Grindl cycle is shown on TS diagram. So what is happening here is this should have been a solid line. Okay. So again, as I said, we are using a liquid suction heat exchanger. So heat is transferred from the subcooled liquid to the vapor, and I am using a perfect heat exchanger. Okay. So when I am using a perfect heat exchanger, the exit condition of the vapor will be same as the inlet condition of the liquid. That means T1 will be same as T3. That's what I have shown in the earlier slide. And what is T3? T3 is nothing but your Tc. Okay. So I am able to heat the refrigerant vapor from the evaporator temperature Te right up to the condenser temperature Tc. Okay. Then what I have to do, still it is at the same pressure. Remember that it is still taking place isobarically. That means the process is pressure is still evaporator pressure only. Next process, as you know, is compression process. Okay. And what kind of a compression process here? This is an isothermal compression. Okay. 1 to 2 is isothermal compression, because you have already attained the condenser temperature. So you have to compress the liquid isothermally from 1 to 2. Previously we had isentropic compressor. So by using a perfect heat exchanger, you can have this kind of a situation where the isentropic compression is replaced by an isothermal compression. What is the advantage of isothermal compression? We shall see in the subsequent lectures that isothermal compression will give rise to lower work input. As a result, you get higher COPs. Okay. So this cycle is known as Grindl cycle. That means a vapor compression cycle wherein the isentropic compression is replaced by an isothermal compression using a perfect liquid suction heat exchanger. Is called as Grindl cycle. And what is the advantage of Grindl cycle is it will give you better COP, okay, compared to the standard cycle. Unfortunately, Grindl cycle is difficult to build in practice. What are the difficulties? The difficulties are mainly to do with achieving isothermal compression, particularly having with very high speed compressors such as centrifugal compressors or reciprocating compressors. Okay. So this Grindl cycle could not be built in practice because of this problem. Okay. But still there is some interest, because using some other types of compressors such as screw type compressors, you can approach isothermal compression. Okay. So still there is some interest in this cycle. Okay. So this is the summary of whatever I have discussed just now. Liquid suction heat exchanger is a counterflow heat exchanger in which the warm refrigerant liquid from the condenser exchanges heat with the cool refrigerant vapor from the evaporator. Thus the liquid becomes subcooled and the vapor becomes superheated. LSHX increases the refrigeration effect, as you have seen already, and ensures only liquid entry into expansion device and only vapor entry into compressor. Okay, so it has the double benefit of ensuring proper operation of expansion device as well as the compressor. So it is generally desirable. Okay. Now let us look at one important issue, that is the effect of suction condition. I have mentioned when we were discussing superheat that when you are increasing the superheat, okay, you are increasing the refrigeration effect, at the same time you are also increasing the work of compression. So ultimately whether it will increase COP or not, I said depends upon the nature of the refrigerant. Okay. Now let us see how do we decide whether it is good or not depending upon the nature of the refrigerant. Okay. That means ultimately we are trying to find out how the condition of the suction means the inlet to the compressor, affect the performance of the system. Okay. So when refrigerant is superheated, usefully either in the evaporator or liquid suction heat exchanger, refrigerant effect increases, as I have already discussed, work of compression increases, specific volume also increases. So whether COP and volumic refrigeration effects increase or not depends on primarily on the nature of the refrigerant. Okay. And there is a method by which you can formulate a criteria. Okay. This criteria was suggested by Ewings, and Gosny has derived useful relations. So let me call this as Ewings-Gosny criteria, and this criteria is used to find whether superheating is beneficial from the point of COP or not. Okay. So this criteria is used to find this, just this. Okay. And this criteria is based on the assumption that the superheating is useful. Okay. So if the superheating is useless, then there is no point in applying this criteria. Okay. Because it's anyway it's bad, right. Okay. So let us again come back to our original pH diagram. So what you have here 1, 2, 3, 4 is the saturated cycle, and 1 2 3 4 is the superheated cycle. Let me begin with let us begin the discussion. For the sake of argument, let us say that this is your expansion process. As you know that the process 3 to 4 is expansion process, and if you are compressing the refrigerant right at this point, what happens? Okay, let us say that this is some okay, so 2 double dash. Okay, so I am compressing the refrigerant vapor immediately after the expansion device. So what will be the COP of the system? Obviously you can see that if you are doing this, QE will be 0 because you are not getting any useful refrigeration effect. Of course W will not be 0, right, that means you are spending some this thing, but you are not getting any benefit, right. So now what happens if this point is shifted, that means the point 4 is shifting, okay, point 4 is shifting in this direction, okay. As you can see that as point 4 is shifting in this direction, the refrigeration effect increases, okay, that means QE becomes non-zero, okay, it is becomes positive non-zero, that means COP will be greater than 0, okay. So gradually COP increases as you move from this point, okay. So COP continues to increase as long as this exit condition lies inside of this, okay, as long as this exit condition lies inside of this, okay. Now you have one condition, okay, that is the condition this for all refrigerants the COP increases between this point to this point, okay, such that the exit condition lies on the saturated vapor line. So with further increase in the enthalpy of the exit condition, whether COP increases or not depends upon the nature of the refrigerant. That means if you are moving this point further right up to the vapor the saturated vapor point and right into the superheated region, okay, will the COP increase or not, because you are seeing that this is increasing and this is also increasing, okay. So up to this point the increase in this is greater than the increase in this, so COP definitely increases, but from this point onward whether this COP increases or not we do not know at this moment, okay. So this is what is given by your Ewing's and Gosney criteria. They have shown that the COP will be maximum inside the two phase region if this criteria is satisfied, okay. So maximum COP occurs when suction state is inside two phase region if COP sat is greater than TE by T2 sat minus TE, okay. That means if this condition is satisfied you will have maximum COP inside the two phase region and any superheating will reduce the COP, okay. And what is COP sat here? COP sat is the COP of a saturation cycle 1, 2, 3, 4, okay. And what is T2 sat? T2 sat as you can see here is nothing but the compressor exit temperature when the compressor inlet is on the saturated vapor line, okay. So what we have to do simply is take the saturated cycle, find out the COP of the saturated cycle for any given refrigerant from the enthalpy values, okay. Then find out the exit compressor exit temperature T2 sat and then find out this value, okay. And if you find that this is greater than this, maximum occurs inside and superheating is bad from COP point of view, okay. Let me show this with an example, right. So this table here it is taken from Gosney and this compares these two parameters, that is COP sat, okay, COP sat and this expression, okay, for different refrigerants, and this data is obtained at minus 15 degrees centigrade, that is 258 Kelvin, and 30 degrees condenser temperature, okay, minus 15 degrees centigrade evaporator temperature and 30 degrees condenser temperature, okay. For example, if you look at ammonia, the COP of the saturated cycle is 4.77 and the exit temperature is 372, that is 99 degrees centigrade, and you find that this value TE by T2 sat minus TE is 2.26, that means this is greater than this, okay. So according to Gosney's criteria the maximum COP occurs inside the two phase region, okay. And whereas for carbon dioxide you can see that this is smaller than this, so there is no maximum. Similarly for R11 this is greater than this, so there is a maximum, right. Like that you can see the values for different refrigerants, and from this you can summarize that for refrigerants ammonia, R11 and R22 superheating reduces COP, and for carbon dioxide R12 and R502 superheating increases COP, okay. So it depends very much on the superheat, okay. So this is what is mentioned here. This I have already discussed, whether superheating improves COP or not. We have to use superheat to ensure only refrigerant vapor entry into compressor and improve volumetric efficiency of compressor, and to prevent moisture condensation on suction lines in domestic refrigerators, etc. Now let us look at actual vapor compression refrigerant cycle and what way they are different from the theoretical cycles. Whatever we have been discussing from now till now are theoretical cycles which do not have or which did not have any internal reversibilities. Okay. Now let us look at an actual cycle. What way an actual system differs from this theoretical cycle. Okay. So the differences are like this. You have pressure drops in evaporator, condenser and liquid suction heat exchanger, and you have pressure drop across suction and discharge valves of the compressor, and friction and heat transfer in compressor, and pressure drop and heat transfer in connecting pipelines, and the presence of foreign matter. Okay, so let me quickly show the actual cycle. You can see that because of all these pressure drops, heat transfer and all, the shape which was like a parallelogram has got twisted. Okay, initially without any pressure drop this should have been a horizontal line, but because of the pressure drop it has become inclined. Similarly in the condenser, because of the pressure drop you have an inclined line instead of a horizontal line. This like this there are various pressure drops, heat transfers and all are listed here. Okay, and we shall see that the effect of all these pressure drops and heat transfers is ultimately to affect the performance of the system. Okay, the same thing is shown on TS diagram here. Okay. Now effect of pressure drop and heat transfer, let me discuss qualitatively. Pressure drop and heat transfer in the vapor line affects the performance significantly by reducing system capacity and COP. That means the vapor line design is very critical and you have to make sure that pressure drop is as small as possible. And normally pressure drop leading to a saturation temperature of 1 to 2 Kelvin in evaporator and 1 Kelvin in suction line is considered to be acceptable. That means there are some standards, you have to design the evaporator in such a way that your delta P corresponds to a temperature drop of 1 to 2 degrees in evaporator and 1 degree in suction line. Now pressure drop in evaporator and suction line depends on layout and type of the refrigerant tubing, velocity of refrigerant and type of refrigerant. And pressure drop can be reduced by reducing refrigerant velocity. However, minimum velocity of 4 to 6 meters is required in evaporator and suction lines for proper carryover of lubricating oil to the compressor. That means you have to maintain certain minimum velocity, okay, even though reduction in velocity reduces the pressure drop. We also see that pressure drop and heat transfer in liquid line is not very critical, and pressure drop across the valves of the compressor can be quite considerable and they may affect the performance adversely. Okay. And heat transfer from the compressor is deliberately provided in most of the cases so as to operate the compressor within safe temperature limits. So in the theoretical cycle we assume that the compression process is reversible and adiabatic, that means there is no heat transfer. Okay. But in actual systems some heat transfer is provided deliberately near the compressor because we do not want to have very high temperatures in the compressor. Okay. Generally the compressors are cooled. Okay. That means the compression process is no longer isentropic but it is polytropic, and generally we define what is known as an isentropic efficiency to find the compare the efficiency of actual compressor with the ideal compressor. Okay. Then apart from this you can also have presence of foreign matter such as lubricating oil, non-condensable gases such as air and water. Okay. And you can also have particulate matter if you are not if your system is not clean in the beginning, and all these things will affect the performance of the actual systems. And the presence of lubricating oil cannot be avoided, but the presence of other things like air, water and particulate matter has to be minimized through proper design and maintenance. Now COP of actual systems can be given by the simple expression which is a multiplication of efficiency of the cycle, efficiency of the compressor, efficiency of the motor into COP of a Carnot cycle. Okay. This is a very rough for a very rough estimation. Okay. And empirical equations have been developed to estimate the efficiency of the cycle, efficiency of the motor, compressor, etc. Okay. Using these equations you can get a rough idea of the actual COP compared to the Carnot COP. Now a complete vapor compression refrigerant system in addition to the basic components consists of several other accessories. We will discuss this later. They are controls and safety devices such as overload protectors, high and low pressure cutouts, oil separators, etc., and temperature and flow controls, and filters, dryers, valves, etc. Okay. So actual system will have a lot many components over and above the basic components. Okay. So let me quickly summarize what we have learned in this lesson. In this lesson we have looked at the performance of SSS cycle, and we have discussed the modifications by means of subcooling and superheating, and we have also discussed liquid suction heat exchanger, and we have seen the criteria for superheat beneficial effect of superheat, And we have also seen the effect of pressure drops or the actual systems with pressure drops and heat transfer rates, etc. Okay. So in the next lesson we will continue the vapor compression refrigerant systems, and we will discuss multi-stage and cascade cycles which are used in very large temperature lift applications. Thank you. Welcome back. In the last two lectures we discussed single stage vapor compression refrigerant systems. In this lecture I shall introduce multi-stage vapor compression refrigerant systems. So the specific objectives of this particular lesson are to introduce discuss limitations of single stage cycles, introduce the concepts of flash gas removal and intercooling, discuss various multi-stage multi-compression systems with flash gas removal and intercoolers, and present a steady state analysis of a typical multi-stage system. And at the end of this lesson you should be able to explain with TS and PS diagrams the limitations of single stage cycles, describe concepts of flash gas removal and intercooling and their benefits, and analyze typical multi-stage multi-compression systems for ammonia and halocarbons using steady state mass and energy balances. We have seen that single stage systems are adequate as long as the temperature difference between the evaporator and condenser is small. This difference is normally known as temperature lift. That means the temperature difference between the condenser and evaporator is known as temperature lift, and as long as the temperature lift is small, single stage systems are adequate. But there are many applications where the temperature lift can be quite high, and the temperature lift can be large either due to the requirement of very low evaporator temperatures and or due to very high condensing temperature. That means there are many applications where for a given condensing temperature you require very low evaporator temperatures. This will increase the temperature lift. There are other applications where the evaporator temperature is not so low, but the required condensing temperature is very high. This also increases the temperature lift. So for these temperature lift applications, single stage systems, we shall see now that they have many limitations. Okay. For example, on the low temperature side, let me give some examples where we can encounter very low evaporator temperatures. For example, in frozen food industries, the required temperatures can be as low as minus 40 degrees centigrade or lower. Typically you have to freeze food products, and if you are talking about quick freezing also, you require very low temperatures of the order of minus 40 or minus 50. Another very typical application where you require very low temperature are in the chemical industries, where really very low temperatures as low as minus 150 degrees centigrade or even lower are required for liquefaction of gases. So these are the two typical applications where you encounter very low evaporator temperatures. And on the high side, if you are using the refrigerant system as a heat pump for heating applications, then the required condensing temperature can be very high. The typical applications of refrigerant system in the form of heat pump could be, for example, in process heating or in the drying. So these are two typical examples where the temperature lift is very high. And in fact, in the last class we have seen that as the temperature lift increases, single stage systems become inefficient. Let me repeat this with the help of TS and PS diagrams. For example, here on a TS diagram we have shown the effect of evaporator temperature. Here condenser temperature is fixed. This is a condenser temperature which is fixed.